Good afternoon, good evening, and good morning, depending on where you are getting me from.
So when it comes to, in this paper, what we actually considered is the voltage calculation, the over voltage. So we used equation 2, which links the voltages at a different location with a transfer impedance matrix. So superposition theorem is applied in this case together with Monte Carlo simulation to obtain the probability distributions of voltages for each customer. So in this paper, we actually used a network with 83 customers. But also one thing that has also to be realized in that the penetration will actually increase from one customer to the 83rd customers. So we have got an illustration of the voltages obtained with the application of the voltage calculation, Monte Carlo simulation, and the transfer impedance using superposition theorem. So what we're actually trying to say is the hosting capacity in this case will be the number of customers of percentages of customers with no overvoltage violation. So once we apply equation 2, we actually obtain the voltage for each customer for the number of samples that are applied. In this case, 10,000 to 100,000 samples were actually applied. So what is applied in terms of the planning risk is the 90th percentile or 10% margin. So this is the black dotted line in this first figure. And then we use a 10% margin in terms of voltage. So 110% is the threshold for which the voltage rise is permitted. And then in this case, I will consider 33 customers or 40% penetration for this network. So if we get the voltages considering the 90th percentile and 110 over voltage margin, then we come up with this figure. So this figure now gives us the number of customers with three-phase solar PV. So increasing from 1 to 33. So the number of customers without violation in this case are denoted by this threshold here, gives us the hosting capacity. So now, since now we are showing the planning risk margin. So a DSO can either be strict or not strict with the planning risk.